Hello. I guess that's my cue. I'd always hoped... Aww. That's very sweet of you, thank you. I'd save your applause until the end because you don't know what nonsense I'm going to spurt out just yet. I had hoped to come out to the Imperial March. Alas, that is not a luxury afforded to me, or at least, you know, London Calling or some kind of credible tunes. But nonetheless, it doesn't dampen my enthusiasm for today. Today has been absolutely lovely. You guys were lovely. So many wonderful conversations, so many interesting things that you're doing, or the ambition that you have to do stuff. It was phenomenal. Thank you, those of you that took the time to chat to me. The speakers, the talks were fantastic. I loved today. I even loved the opening keynote, or as we think of it in Neo terms, the inferior keynote. Obviously, it's a factional thing. But look, I mean, the demos were great. Emil did a great pitch. But I was sitting towards the back in that. I did somewhat wistfully think, though, when I saw my colleagues and friends on the stage, you know, what would it be like to be on that stage, to be on a stage with a database technology executive of such prowess, who's been and done things that are so impactful, that have changed so many people's lives, someone who just has an extraordinary level of charisma, someone that we can all look up to. And now I know, right? So it's really awesome, actually. If you're wondering, that's Emil's bête noire. That's Larry Ellison, who is a former CEO of another database company you might have heard of. Am I fired? Yes. This is always a slight battle there. So what we're going to talk about. So I'm going to do a little bit of a kind of humanely technical ending, joined by a few friends on stage to talk about some of the amazing thing that's happened in Neo4j since you last saw us, which I guess in New York was awfully 4 years ago. So we're going to do a cheeky little bit of computer science, nothing too taxing. Don't fret, I'm not going to make you do algorithms classes or something, but just a little bit of computer science so we can figure out what kind of data structures and algorithms are suitable for different kinds of database purposes. So nice friendly bit of database research there, academia there. Then we'll come up a level, we'll do a little bit about database architecture. Don't worry, it's all humane and friendly. There won't be a quiz at the end, but if there was a quiz at the end, you'd pass it because you're all brilliant, wonderful people. Then talk a little bit about why Neo4j is graph native. You've heard this the theme a lot throughout today, and why it matters. And I'll be asking my colleagues, Alistair Jones and Tobias Lindorker, to come and join me on stage for that, to talk about some of the technical depth in why that matters. And tell you, in terms of numbers, why graph native gives you such astonishing performance, such astonishing, it's just an astonishing engine for building ambitious applications. And then we'll go party, right? Sound reasonable? Yeah! Front row, I like you. People towards the middle, up your game, right? You're a bit further away. Okay, you're the cheerleader for the middle. Beard guy, you were here yesterday and I love you. Everyone, when Beard Guy cheers, we all follow Beard Guy, right? I'd walk into a fire for this man. Unfortunately, his beard would be massively combustible, but it would... anyway, look, so that's the kind of textual bit of what we're going to do. If you're wondering, I do have an artist's impression of how this will look. So, thank you, Nigel, for that flattering image. So, damn it, my clicker won't advance it now. Native, what's native? When I think about things that are native, they are... took this definition from Wikipedia, the font of all knowledge. But I think Neo4j database fits this definition. We have a small number of modules, each of which is dedicated to some part of the overall process of graph storage and query. And as we build out the rest of the graph platform, we will maintain this kind of native philosophy where we will build as small a number of well-attuned, well-defined modules as possible in order to provide an amazing experience for graph workloads. So this is our working definition for native, and I hope to convince you in the course of these few minutes that native is good and it's well worth upholding. So let's do a little bit of computer science. What do you reckon? Yeah? You see the... No? Oh. No? More like it, maybe? Okay, we'll settle with this one. Shout out to the geeks. So look, here's a linked list, right? Simple, humble, unordered, singly linked list. And this list has properties. And what are the properties of this list? Well, it turns out it's really easy, really cheap to add something to the list. And it's relatively less cheap if you want to find something in that list, because it's unordered. So, you know, in computer sciencey terms, we'd say that it's a constant time operation, an O1 operation to add to the list, and it's a linear or ON operation to read that list, to find something in that list. So, yeah, it's kind of good for uncontended writes, and it's kind of, you know, pretty mediocre, really, for reads. But, you know, knowing those properties, we might be able to build a database. And if we put a box around our list and we put a nice client API on it, we could kind of squint at it and say, hey, that's a database. And the properties of that database is that it's rather good for uncontended writes, and it's rather poor for reads. It's relatively slow for reads. So this database would be native for that model, for uncontended writes and not so great for reads. If we try to scale that out to a multiple clients interacting with it, a contended write scenario, we know that mechanically that wouldn't be very sympathetic. This would be quite a naive approach where all of these clients would contend for access to the part of the data structure to which we're going to write. We can get around this. We can do all kinds of clever stuff mechanically. We can do things like the disruptor pattern, so have all of our concurrency controls run in user space very quickly. We can use things like CRDT. So CRDT is a data structure. It's a conflict-free replicated data type, a data structure that has well-known merge rules. And in this case, what would happen is each client has its own unordered singly linked list, writing away into that. Then at some point you merge them all together, and you get a bigger unordered linked list, thereby solving the contention problem. So now we could have a database that's pretty good for even contended writes and still relatively mediocre for reads, right? But that database has a native model, right? So far, so good. I wouldn't, for what it's worth, you entrepreneurs in the audience, wouldn't necessarily go recommend that you commercialize this. I don't think it has a great deal of commercial viability out there in the real world. Cool, but we're database people. What do we know that's a bit better than a linked list? Trees, right? So we know that we can insert into trees and we get some kind of ordering, which is lovely. What happens when we've got trees is that the properties are such that we have log n for both read and write. And that means that while writes are technically less performance than they are in the singly linked list case, reads are a lot better. When we do log n, it means that at each step through, we throw away half of the search space. So for a tree of 1 million, it typically takes us only 6 hops to find where we want to go. This is great, right? So now we can start to think about building a database around a tree. And we'd have log cost access for reads and log cost access for writes, at least in principle. I mean, we know that there are mechanics that go on and rebalancing and all sorts of other fun things. Databases love trees, usually. Classic B trees are the thing that I think we all learned in college, where you kind of have an index structure in your non-leaf nodes, and then your leaf nodes become your actual data values. And we've seen things like B plus trees, where you can do linear scans along those leaf nodes. So this is great. But if you are trying to take this data structure and apply it to something that needs to resolve many lookups in the tree in order to achieve some informational goal, rather than simply retrieve a document or a row or what have you, then you get lots and lots of these logs. I know, right? Wah, wah, wah. Pity me, pity me. So that's relatively expensive. If I've got a graph, for example, a graph, which is what I'm interested in, of millions or billions, each one of these lookups could cost 9 IOPS. And if I want to explore 1,000 hops in the graph, that cost me 9,000 IOPS. That's an awful lot of IO activity just going on to find some, what I think of as a relatively modest graph search. Neo4j doesn't have many logs. The puns do get worse from here on. That's just like, fair warning. If you're coming with me on this journey, you're going to be kind of groaning on the way out. Neo4j doesn't have many of these logs. We do have some indexes that are tree-based, but we use them relatively sparingly. We use these tree-based indexes to find starting points. So we use relatively minimal log cost lookups. And then once we're in the graph, we do traversals at cost 0.1. Ultimately, what does this mean when you are trying to build a database? Well, it means you've got to pick the right tool for the job. You've got to pick the right kind of algorithms and data structures to suit the data model that you want to support. Inside Neo4j, we make choices that prefer graph workloads, so we choose the right algorithms and data structures to suit those workloads. Inside Oracle, I imagine, they've picked a bunch of data structures and algorithms that suit the relational workload. I'm sure the same is true for all the kind of competent databases out there. But no matter how much you bash away at your database and try and turn your relational store into a graph store or what have you, you're still trying to hammer in a screw. It's just not the right tool for the job. You're going against the grain. Now, all databases have a native model. For Neo4j, that's graphs. For MongoDB, that's documents. For Oracle, that's relational. For Cassandra, that's columns. And actually, I do think that each database is generally very good at its native model. There are a few stinkers out there, obviously, but generally we find that these databases are good at their native model. But when you try and impose a non-native model into that ecosystem, it's kind of unloved. It goes against the grain. This is a sea lamprey. Residents of New York State, this costs you $500,000 a year to keep under control because it's non-native. It doesn't work well with the local ecosystem. It messes things up. It's unloved, and by God, it's scary, actually. So when you've got this kind of opportunistic multi-model thing, you have to worry about it being sea lamprey-like. It doesn't compose easily. It's not natively supported in the database engine. It's kind of an add-on. So you've got to think, well, why would people do that? They've got a perfectly good native database for a particular model. Why would they then want to kind of bolt graphs on? And the answer is, as we saw this morning, it's this. Why would we jump on the graph bandwagon? Because graphs are amazingly popular. And year on year, for several years now, they have been by far the largest growing category of the entire data space. And of course, if you are a database vendor and looking at this chart, you'd be thinking, yeah, we've got to get us some graph here, because that's where all the action is at. It's a bit bandwagon jumping, really, but I can imagine if I was in a different database, I'd be like, hey, hold my beer, I've got this graph stuff, looks pretty easy, that guy Emil can do it, I'm pretty sure I can do it. All right, joking aside. Am I still on safe ground? Still on safe ground? He's a really nice boss, really. Let's talk a bit about architecture. My goodness. What a town in which to talk about architecture, right? It's just phenomenal. Just amazingly. What? Too soon? Too soon? Okay. Let's talk about architecture. Cheap laugh, yeah. No, I've already gone through all the Brexit nonsense with some of you, so we're square. In terms of what's going on in database architecture, well, we see that there are two non-native approaches to graph, these kind of non-native architectures. One, we call graph layer, where you take an existing data store, something like Cassandra, for example, and you glue on top of that some graph API, and then declare victory. So, hey, now it's a graph, because look, the API says node and relationship, or edge and vertex if you're feeling particularly academic. The other side, we see this thing called graph operator, where I've got an existing database with a query language, and we kind of enrich that query language with a bit of, a few keywords that say like graph something, and then declare victory, because now you can do graphs and you're multi-model and you're feeling pretty good about yourself, right? I think there are genuinely both computer science and architectural concerns about this. So first and foremost, the non-native databases we see out there now, they have no cipher, despite the valiant efforts of OpenCipher to bring the cipher love everywhere, and maybe they will get cipher. But right now, they have no cipher. They have their own ways and idioms of doing things, which may be fine. It may be very clueful. I couldn't comment. But what they do is they lock themselves out from the world's largest community of graph data skilled people, the world's largest community of tool ecosystem, and so on. They're kind of on the outside of where all the fun's happening because they don't yet buy into cipher. In the middle tier, kind of glue tier, you've got some really interesting things happening. In the graph layer architecture, you've got this level where you do a bunch of denormalization. So effectively, you're mapping between the graph API and its kind of nodes and relationships and properties model down to some other model, the native model, for example, columns. And that graph layer has to be able to translate between those two worlds. And in doing so, it also has to make a bunch of upfront design decisions about the nature of the graphs that you're going to be running on it. How deep are these graphs going to go? Are they going to be big and flat, or what's the degree? What's the kind of what's the nature of these graphs? And it turns out that that's a really hard thing to pick in advance because graphs are really heterogeneous, right? They come in all kinds of shapes and sizes. So what do? You maybe look for guidance from what you think is like the world's biggest graph. What's the world's biggest graph? I don't know, let's say Facebook, right? That seems pretty big. And what have they got? Well, we know that everyone on Facebook is only like 3 point something hops away from each other. So that's fine, let's denormalize for 3. Let's make sure, because most graphs, even the biggest, most challenging graph, the Facebook graph, that's only 3 point something. Let's say that we'll denormalize our graph so that it supports traversals, efficient traversals up to depth 3, because nobody's going to want to traverse more than depth 3, because Facebook don't, right? So that seems like a good idiom. Until you traverse to depth 4 or depth 5 or depth 100, in which case you've fallen off a performance cliff edge, which is terribly worrying. On the graph operator side, you've now got this kind of subtle interplay between the keywords that you have in your query language and the data you're storing. You have to start to maintain conventions. So you have to ensure that the data that you're storing is in such a shape, has such, for example, form fields on it, so that the graph operator has some purchase on that data and it can reify the graph out of it. If you don't abide by that convention, then your graph simply doesn't come together. The database engine doesn't care about graphs. It has no way of saying, hey, you can't leave a dangling relationship there. It's just like, yeah, fine, that's just a document, I'll store that, that's awesome, thank you. There's just nothing safe for you there. So the underlying engine doesn't really help. Ultimately, these engines don't understand graphs. So you can't prevent things like dangling relationships or half-formed relationships where one node thinks there's a relationship and the receiving node doesn't. Because the engine doesn't know about graphs, it can't enforce them. What does this lead to? You get logical corruption, where you've got these kind of half-dangling relationships. But what you'll do based on that is you'll write more data back into the database. Right? So you'll get this logical corruption will spread. It'll spread through the graph. So ultimately, when you're placing your data in these kind of databases, you have to be aware of these kind of pitfalls. And they really are serious, right? They really are serious because the underlying engines aren't designed for graphs, they're designed for something else. So the graph layer drawbacks, this is some Japanese knotweed, beautiful, native to Japan, not native to London where I live. In fact, if you've got this in your garden in London, you have to like dig a hole so deep to get this stuff out that you could deliver it back to Japan through the Earth's core. It is so horrifically invasive and non-native. So the graph layer drawbacks are that the engine and the store, the way they lay out files on disk, just aren't about graphs. They're for some other data structure. Graphs aren't the motivating workload. So if you're a graph user here, and you think, yeah, I really want this feature, get to the back of the queue, because the motivating workload is documents or columns or keys and values or whatever, and 99% of the user base for this system is going to want the good stuff to go on that data model, and you're just like one of those, in the wings graph people, but we'll get to you eventually, but you're not getting the love. Denormalization doesn't work. You get past the limits of denormalization, and your performance falls off a cliff edge. Then you've got a bunch of operational stuff. You've got schema rigidity and evolution problems because none of the underlying engine is really aligned for graph work. Internally, we often see these things are implemented by hash maps. Right? Hash maps are fine. If you're building a column store or a KV store, super beneficial to use a hash map, because that hash function has the useful feature, the useful behavior, that it spreads data around, which is exactly what you want to do. In graphs, that's exactly what you don't want to do. You want to keep locality together for performance reasons. So this data structure, not only is it lying to us in computer science terms, because pathologically these are order n squared, not order 1, but actually the hash function itself is doing something that's detrimental to graphs. It's spreading data around. It's not locating data together where it can be cheaply accessed for traversing a neighborhood. So, Himalayan balsam, pretty plant. Again, non-native in the UK where I live. The graph operator drawbacks are that it only works by convention. Right? It's kind of a convention-driven development. Again, the underlying DBMS can't enforce graph integrity. So if you really do feel the value of graphs, why would you store something in an engine that can't enforce graph integrity? It's like, it's not really a database. It's more, if a database is an analog of a filing cabinet, this is an analog of a shredder, right? It just really shreds your graph. The underlying data formats, store formats, and so on are designed for another job entirely, another workload entirely, not motivated by graphs. And so again, you get those same kind of performance concerns. Typically, these things are implemented by B trees, which are either Bayer trees or Boeing trees or balance trees. We don't actually know what the B stands for, which is kind of hilarious, but we all know what a B tree is. So you've got this, this tree-like access. But the underlying model knows nothing about links, knows nothing about relationships. You have to kind of reify or compute out your graph by traversing that tree at log cost. It's super expensive. What happens when you delete a document that some other document referred to? Does the database know magically how to go all the way over here, maybe brute force scan the whole thing and say, hey, you used to be referred to, I'll now remove that link? No. This is all by convention. This puts work on you, the user, when you should be getting on with doing the important stuff, right? Which is like doing kick-ass graph things. So do one thing, do it well. This is our philosophy. We at Neo are extremely and exclusively motivated by graph workloads. Everything we do, every change we make to the software is because we consider graphs being poured up on us in like a graph. This is an odd thing to be doing in front of hundreds of people. I'm sorry. But it's like graphs, pouring graphs everywhere, right? And we are motivated. Every change we make to the product is because we want to make your experience working with graphs better. So look, there was some computer science, bit of engineering, architecture consideration. And, we hope that, because we care about those things sincerely, that you get a really great experience with Neo4j. For now, I'd like to call Alistair Jones to the stage, and he's going to talk about what's gone on in Neo4j 3.3 so that you really can take our learning in database architecture and computer science and apply it to the kind of real-world problems that you're working with. Alistair. Woohoo!
Thank you. Thank you, Jim. I'm going to talk about two things that people do with graphs. So, first of all, we see a lot of people doing transactional workloads, doing online transaction processing. It's a classic thing that people are doing with Neo for years and years. Secondly, actually, what LTP typically means with a graph is visiting small sections of the graph, reading or writing small parts of the graph in each transaction. Secondly, people are also doing analytical processing with graphs. So that typically means a much bigger part of the graph, maybe even the whole graph you need to look at to do some analytics. Now, OLAP outside of graphs, we've come to know over the last couple of decades that the conventional wisdom is really to go for specialist OLAP technology. So you probably want a different type of database to do your OLAP. You probably want an ETL workflow to get your data from your transactional online system into your analytics system. And that's just how we expect it to work. But recently, there's something like a new way of thinking about this. There's something been coined as HTAP, So this stands for hybrid transactional and analytical processing. So the idea, I mean, just in this Venn diagram here, the idea is that you can have the same data model, the same, ideally the same technology, and you can do a mixture of both the OLTP and the OLAP workloads. You can do your transactional live stuff, your e-commerce, and you can do your analytical, much bigger workloads at the same time. What's the motivation for doing this? Well, the primary one is actually about being up to date, about being able to respond quickly when the data is changing. So you've made a sale, you've got a sudden trend, a sudden spike that's going on out in the real world. You need your analytics to be able to respond to that quickly. You just can't wait for a massive, wait for a massive ETL pipeline to run through to get the data into your analytics world. The other side is simply just complexity. Like, do you really want to have a whole totally separate system that's going to have all of this data in it? So this is a nice idea. Can we do it in, how do we do it in Neo4j? Well, let me show you a picture of a Neo4j architecture. So since Neo4j 3.1, we've had an architecture where you can divide up your cluster. So you can say, some of my cluster, I'm going to call it the transactional part. Some of my cluster is going to be for read operations to get massive read throughput, read scalability. In 3.2, earlier this year, we went a little bit further. So we said, yeah, actually, you can have these categories. We'd have some more specific categories as well. You could use those for having different regions, for example, or specific data center characteristics. Actually, what you can also do is you can say, some of my servers, I'm going to use those for OLAP, for doing that analytical processing. Now, I can treat these, they're all part of the same cluster, they all have the same data model, the same data in them, but I'm actually able to put, direct load and to have specialized servers. So I can have, if I really want a load of CPUs or a load of RAM in that OLAP stuff, to do that OLAP workload, I can just have those machines and incorporate them into the same cluster, have all the same workload. And this kind of little topology, these gray lines you can see here, actually it's not only is it taking that workload, but it's also isolated from the transactional workload. It's not going to affect your transaction processing, your online stuff, when you're doing one of these massive analytics jobs. All you're doing is occupying those big machines for that workload, leaving the rest of the cluster totally fine and keeping your website going. Okay, so how do you actually do this? How do you configure this in Neo4j? So you can do it right now. You do it through configuring applications, basically. So here I've got an application on the left, the OLTP application, and on the right, the OLAP application. Both of them include this part of the system, kind of part of Neo4j, and Neo4j drivers. And in those drivers, through configuration, I can just direct load to the right part of the cluster. So make sure my OLAP work, my analytical work, goes to those big high memory machines. How do I do this? It's just in configuration of the driver. I can say, this driver is for my OLAP stuff. And on the server, I can specify a policy. I can say what groups of servers that policy directs load to, and then what servers belong to those specific groups. So if you put that back into the architecture here, that configuration is going to make this routing go exactly to the right server when it's needed. In fact, I don't even need to have separate applications. I could just have one application that does a mixture of transaction processing and analytics. Maybe it's that system that is recognizing the new trends, the new burst of sales in a particular area as an analytics job, and then it's taking action to actually change the website to account for that. So let's have a look at what we do in the analytics side of things. This is a model of how we run work on Neo4j, how we do queries. So Neo4j is all about having an application. It sends Cypher, which is processed by a query engine, and that accesses the graph model. But we could add something else to be even better for analytics beyond this capability. And what we've already talked about today, what we're going to add in is graph algorithms. This is how I think of algorithms. I think of massive graph, probably whole graph. Magic happens in the middle, some kind of graph algorithm. And out of the other end, I get actionable, actions that I can take. So that could be an identified fraudulent, suspicious transaction that I want to investigate for fraud, or it could be an insight like this new business strategy that I can recognize a cluster of customers who are acting in the same way, and actually I want to realign my business around that. That's a much longer term kind of insight. But the common factor is this graph algorithms in the middle. The types of graph algorithms that we're releasing today with 3.2, there's 3 categories, and I've just got a little like a picture to try to explain what each of those is about. Centrality is about nodes that are significant according to their position in the network. So it's things that you route through a lot if you're traversing in general across the network. That's a really significant part. Clustering is about dividing the whole graph up into sections, into clusters, so identifying grouping in the cluster. And finally, pathfinding. I think that's what we intuitively think of in graphs, about finding your way across a map or through a system of streets, finding my directions across the city. And there is a range of algorithms. This is classic graph theory stuff, and they're all available for this OLAP workload through the graph algorithms. So that's what you can do. How does it fit into the picture? How does it work inside Neo4j? This is the picture we had before, and we get the graph algorithms, we put them alongside the Cypher query engine. So the nice thing about doing this is that we've kept them totally inside the same API. So all of that infrastructure, all of the way that you've written your application, it's already sending a transactional workload. It still works. It's still the same thing. You can just you've just upgraded from Cypher to Cypher plus these whole graph algorithms. And how do you switch? Well, it's just sending different Cypher queries. On the left, it's like a normal kind of writing a bit of data. On the right, you're doing a huge bit of algorithmic work. Okay, now we're going to dig into one of the algorithms in particular. And the one I'm going to choose is PageRank, because that was on the top of the screen anyway. How PageRank is defined is, well, what's it for, first of all? It's for working out important nodes. It's like what's important in the network. And why are they important? Well, they're important because important pages link, or important nodes in the network are connected to those important pages. That's a bit kind of circular, like it's important because something else is important. That's quite hard to compute, to work out the answer to that. You have to solve it through an iterative method. And the point of saying that is that if you think about what's got to happen in the software to solve this, we've got to look in the graph, we've got to consider every single node and every single relationship, and we've got to consider them multiple times because we need to go through the network to stabilize, to solve all those many simultaneous equations to find the values for the importance number that are going to make the whole system stable. So it's a lot of work. And a little animation of that happening. You can see some of the nodes, they're all equal, but just based on the structure, we can derive information straight out of that. We can say, these are the significant nodes. And I'm showing them like getting larger and redder in this picture. Okay, let's try using something kind of like a real-world graph. So we're going to use DBpedia as an example. So DBpedia is the project that extracts a database from Wikipedia. And we're thinking about, right now, the graph of Wikipedia pages and how they link to other Wikipedia pages. And people have been pretty busy, those guys writing Wikipedia. So thank you, Wikipedians, for writing 11 million pages. So in this graph, we've got 11 million nodes and 116 million relationships between those pages, links, basically. So we want to do page rank on this. Sounds like a pretty big job, so we better call the power plants to be ready for the processing here. We're going to spin up 1,000 servers and get ready to do this. Or we could just do it on one server. Yeah, let's do that. Actually, that's all we need. We don't need a whole server farm. We don't need a data lake. We don't need anything. Just a single or one new server will be perfectly sufficient. We can. It's useful to have a lot of CPUs though, because this is a massively parallel operation, and actually, whatever hardware we have, we can make use of. Okay, so 11 million nodes, 116 million relationships, 20 iterations. That's what we need to get like stability in this kind of graph. And how long does that take? Less than 10 seconds of computation. Okay, so it was actually quite easy, all of that massive computation. It's so fast that very, very easy. Great. With that, I'm going to hand back over to Jim. Well, I hope you really, I'm really excited to see what gets built with this stuff and see this in a hybrid application.
Wonderful. I mean, absolutely underwhelming that you can crunch through such a lot of data in 10 seconds, right? I really want to build a big Macho cluster of 500 servers. Yeah! But one new server, 10 seconds, phenomenal. So this HTAP stuff is brilliant, right? Your Neo4j system, that's Stefan Armbruster's Raspberry Pi system, in case you guys saw it in the dev earlier. You can combine your LTP and OLAP stuff into the same cluster. It's super, super convenient. I think it's really cool when you're now mixing all this with graph algorithms. But the thing that unifies all of this, the thing that's the beating heart of Neo, is Cypher, the Cypher query language. And so I'm going to invite Tobias Lindorker onto the stage to talk about some of the improvements we've made in Cypher. Tobias.
Thanks, buddy. I was supposed to get the introductory slide. You didn't click this forward to me. Yeah, so me and my team are at Neo4j are continuously working on making Neo4j much better and more native at running Cypher. And I like to think about these queries that we run for you all as little anthropomorphized things. I tend to anthropomorphize code, and I do it with queries as well. So this stick figure is going to represent queries throughout this section of the presentation. So Cypher is about, as you know, running queries on graphs, over graphs, on modern hardware. Or it could be with that one new server that Alistair showed. But it's about running queries on modern hardware. And as I said, we're working on making this more native. And when we talk about being native, when it comes to graph querying, what we're really talking about is being it's all about being the graph being native to the machine that it runs on. This is the area that we're native to now. It kind of looks like a motherboard at night. It's kind of cool image, I think. And it's about mapping these, having data structures that natively represent your graph, and being able to implement queries efficiently on modern hardware to run over those data structures and process that graph. So in Neo4j, in version 3.3, the version we're releasing now, we've taken steps to make it more native to execute graph queries on hardware. So we're being more native to graphs and more native to current hardware. Really, as I said, it's about the data structures. So we are reinventing the data structures and representations in use. So we're moving away from the general purpose built-in Scala and Java data structures and building specific data structures and representations to handle our graph workload. It's really about fitting better with the workload that we're executing. One example of that is how we access variables in Cypher, how we access data in the Cypher runtime. Where it used to be like this, where there were indirections between the executing query and the valuable stuff, the executing query, of course, the stick figure on the left, and the valuable stuff, the goal on the right. There were indirections, which is like the CPU having to open a big locked door in order to get to the valuable stuff. So what we've done now is and there's also a bit of computation here going on in order to find which value I'm actually looking for. So what we've done now is we've moved that computation to compile time, and that allows us to remove the indirection. So now we got direct access to the valuable data. And this simple change gives us noticeable performance improvements. Just simple stuff like that. Here we see a flame chart. This is something we use extensively. Each of our benchmarks that we run continuously over the database multiple times a day emit one of these for every query that we benchmark. So this is a particular query. This is showing the different parts of that the query is doing over the database as it executes. So we've spent a lot of time in Neo4j 3.3 taking a holistic view of make queries run.